In problem number 2 in section 6.3, we're going to toss a coin 2 times and observe the sequence of heads and tails. Now, each of the 4 outcomes has the same probability, and in this section, we're dealing with sample spaces that are called equally likely, and that means that every element in the sample space is just as likely to occur as any other. So you toss a coin twice and observe the top face. Here's what could happen. You could get a head and a head and a tail and a head, right? No particular order, or a tail and a tail. There's the sample space, and each one of these events is just as likely as any other. Part A asks us, what is the probability of this event, getting a head on the first and a head on the second? So look up to our sample space. We've got 4 elements in it. Exactly one of them is that event. So the way I like to do these problems is, you know the probability is a fraction. I like to get the bottom number first, the denominator. That's the number of elements in the sample space. Matter of fact, I'm going to write this. It's the number of elements in the event divided by the number of elements in the sample space. We have 4 elements in the sample space and 1 element in the event. And there's our probability. And in part B of this problem, we want the probability of getting at least 1 head. So I'm going to take this at least. Now we're going to see this somewhat often. This at least business, I'm going to write this like this. How do you get at least 1? Well, you could get 1 head, or you could get 2 heads, right? You can get, if you toss it twice, you can get exactly 1 head or exactly 2 heads. So let's write this event here in terms of exactly how could you get this? Exactly how, and then how could you get exactly that one there? This is going to be the way I see it. 1 head you could get like this. You could get a head and a tail, or you could get a tail and a head, and plus, you could get exactly 2 heads. And 2 heads, you can only get a head and a head. In the first, we're going to have, out of 4 elements in that sample space, we're going to have 2 plus. The plus comes from this or. And in the second one, the probability of 2 heads is 1/4. So we're going to end up here with 3/4 as our probability. In problem number 3, we're told that we roll 2 dice, a red one and a green one, so we can distinguish them. And we want to know, what is the probability, this is part A anyway, that the numbers add up to 8. Well, I see in this case that there are 36 possible things that could happen in our sample space. So if we wrote it like this, here's 1 die, 1, 2, 3, 4, 5, 6, and the other die, well, let's make a little bit more room there for that one. Let's put our 6 over here. And then we could have a 1, 2, 3, 4, 5, 6. I can distinguish these 2 dies. Maybe this is the red one, this is the green one. So here's all the things that could happen here. We could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, and then we could get a 2 and a 1, a 2 and a 2, and so on and so on. And finally, we get down in this corner, we could get a 6 and a 6. So altogether, there's 6 times 6. There are 36 outcomes in this sample space, and we're looking for the elements that add up to 8. So how could we get an 8 here? We could get, say, well, what could we get? We could get, let's look at these numbers here, see if we can work this out. What if we get a 1? Well, to get a 1, if we got a 1, we need a 7, and there is no 7. We could get a 2 on one die and a 6 on the other. That would work here. So we could get a 6 and a 2. We could get a 5 and a 3. We could get a 4 and a 4, a 3 and a 5, and a 2 and a 6. So the probability that these numbers add up to 8, that the sum is 8, this is going to be 36 elements in the sample space, and let's count here. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5 ways that event can happen. That's our probability. So what we expect here is that if we were to perform this experiment 36 times, we would expect about 5 of those 36 outcomes to be 8s. In problem number 4, we're told that a state is selected at random from the 50 states. What is the probability that is one of the 6 New England states? Well, look, now there's only 50 states possible, and 6 of them are New England states, so I think this one is done. And problem 5 says that the modern American roulette wheel has 38 slots, which are labeled 1 through 36, between red and black, and plus 2 greens, a single zero and a double zero. So there's 38 slots altogether. What is the probability that a ball lands on a green number? All right, well, the probability that it lands on a green, there's 38 slots altogether, and 2 of them are green. In problem number 8, there's 4 parts here. Each part has 3 elements in the sample space, right? The sample space is this one right here. S equals element 1, element 2, and element 3. Now, here's what we're going to be doing. We're going to take our 1 unit of probability, and I like to write it as like this. So I have 1, here's how I imagine this. I have 1 square unit of probability. And what I want to do is distribute this 1 unit of probability to this element, and this element. So if we distribute it, maybe I can figure out a way to take this much probability, put it here, maybe this much probability, and put it here, and this much probability, and put it here. So this is called a probability distribution, because I'm distributing this probability to these elements. So here's how we could write this distribution. We could write it like this. Here's our S, and here's our P of S, and our S's are S1, S2, and S3, and our probabilities, okay, now this is going to come from problems A, B, C, and D. So let's fill this in here. Well, before we fill it in, or as we fill it in, what do we know has to happen here? We know that these numbers are these numbers here, and these are probabilities, so we do know this. We do know that for each one of these S's, number 1, for each S, this has to be true. 0 less than or equal to the probability of that S less than or equal to 1. Right? These are numbers here. They can't be we're taking this much area out of here. They can't be negative and they can't be greater than 1 because on total we have 1 square unit. So each one of these numbers that we put over here has to be between 0 and 1. The second thing that has to happen is that when we sum these numbers, now this symbol right here, this is a capital Greek letter sigma, and sigma starts with the letter S, and so does the word sum. So this is just a symbol that says add up these things here. So if we add up those probabilities, right, add up these, we should get exactly 1. And that should make sense, because if we distribute them back out and then put them back, we should be back to our 1. So for a distribution to be a valid distribution, both of these conditions have to be satisfied. And if one of them fails, then we can say that this distribution is not a valid probability distribution. Now in part A, we're given that probability of S1 is 0.4, probability of S2 is 0.4, probability of 3 is S4, and what we want to do is determine if this distribution is or is not a valid probability distribution. So to do so, let's just go through our 2 conditions. If both conditions are met, we have a legitimate valid distribution. So number 1, we can see that, and I'm going to note this, for each one of those S's, it is true that 0 less than or equal to P of S less than or equal to 1. So condition 1 holds. Condition 2, if we add up these P of S's, we get 0.4 plus 0.4 plus 0.4, which is equal to 1.2, which is not equal to 1. Condition 2 fails. I'll note that. So I will even say since condition 2 fails, this distribution is not a valid is not a valid probability distribution. Let's just go on to part D. Let's see this. We have to look at our two conditions. So the first condition, you can see here by observation that for each one of these S's, the corresponding P of S is between 0 and 1. So we'll state that for each S, this is true. 0 less than or equal to P of S less than or equal to 1. And now, let's go on to condition 2. What about this? What about the summation of these P of S's? Well, this turns out to be this plus this, right? Let's just add up those P of S's. So 1/4 plus 1/2 plus 1/4. And sure enough, this is equal to 1. So let's say this. We'll say, since both conditions are satisfied, or both conditions hold, this distribution is a valid probability distribution.